Here is something worth thinking about as you settle in tonight. You have probably heard the word torque before. Maybe someone mentioned it while talking about a car engine. Maybe you saw it on a tool or in a vehicle specification and moved past it without giving it much thought. That is understandable. Torque sounds like one of those technical words that belongs in a garage or a factory or an engineering textbook. But once the idea really clicks, you start noticing it everywhere. It is in the way you open a heavy door. It is in the way a wrench loosens a stubborn bolt. It is in the way a car climbs a hill, the way a helicopter rotor cuts through the air, the way a bridge resists bending under the weight of a train, and even the way a building quietly holds itself together while you sleep. Torque is simply a twisting force. More precisely, int is what happens when a force to rotate something around a point. And the most important thing to understand is this. Torque depends on two things: how hard you push and how far from the pivot point you push. That is the whole secret. Imagine a massive old wooden door, the kind you might find at a cathedral or an ancient courthouse. If you push that door close to the hinges, it barely moves. You can lean into it with real effort, and it resists you. But if you push near the handle, far from the hinges, the same door swings open easily. Same door. Person, almost the same force, but a completely different result. The difference is distance. When you push farther from the pivot point, your force has more rotational effect. That is torque. That is why door handles are placed as far from the hinges as possible. That is why a long wrench makes it easier to loosen a bolt. You are not necessarily becoming stronger. You are letting geometry multiply your effort. And that idea, that geometry can amplify force, is one of the oldest and most powerful ideas in engineering. The ancient person who probably understood this best was Archimedes. He lived in Syracuse on the island of Sicily around the 3rd century BC. Most people remember him for the famous story of running through the streets shouting "Eureka" after realizing how to measure the volume of an irregular object. That story may have been exaggerated over time, but Archimedes himself was very real, and he was one of the greatest mathematicians and engineers of the ancient world. He is the one who reportedly said, "Give me a lever long enough and a place to stand, and I shall move the world." That sounds poetic. But Archimedes was not simply being dramatic. He understood that a lever is a torque machine. The fulcrum is the pivot. The force is applied at some distance from that pivot. And the longer the lever arm, the more turning force you create. A small person with a long enough lever can lift a weight that a much stronger person could never move by hand. Archimedes described what we now call the law of the lever. A system is balanced when the force on one side multiplied by its distance from the fulcrum equals the force on the other side multiplied by its distance. Simple, elegant, and absolutely everywhere. It explains seesaws, scissors, crowbars, pliers, scales, and the way your own jaw works when you chew. It explains why ancient builders could move stones far heavier than a human body. It explains why a tool can make a person seem stronger than they really are. But Archimedes did more than think. He built. During the Roman siege of Syracuse in 214 BC, Archimedes designed machines that helped hold off the Roman fleet for nearly 2 years. Ancient sources describe cranes that reached over the city walls, grabbed Roman ships, lifted their bows out of the water, and dropped them back into the sea. Just imagine that scene for a moment. You are a Roman soldier. You have crossed the Mediterranean. You are approaching the walls of Syracuse in what you think is a powerful warship. Then, from above, a huge mechanical arm swings out, hooks the ship, lifts it, tilts it, and suddenly the deck beneath your feet is no longer level. To the Romans, it must have felt almost supernatural. But it was not magic. It was torque, long arms, pivot points, counterweights, stored energy, rotational force, amplified and directed. Archimedes never used the modern word torque. That word comes from the Latin torquere, meaning to twist. But the concept was there. The physics was there. Human beings had discovered that the world could be moved not only by strength, but by distance, angle, balance, and design. Now, torque can be confusing because most of us first learn about force in a straight line. You push an object and it moves. Push harder and it moves faster. A heavier object is harder to accelerate. That feels intuitive. Newton would later give that idea a formal equation. Force equals mass times acceleration. But torque adds a twist. Literally, it is not only about how hard you push, it is about where you push. It is about how far from the axis you apply the force. And it is about the direction of that force relative to the pivot. If force makes things move in a line, torque makes things rotate. And once objects begin to rotate, another idea enters the story. Moment of inertia. A simple way to feel this is to think about a figure skater spinning on the ice. When the skater stretches their arms outward, they spin more slowly. When they pull their arms close to the body, they suddenly spin faster. The skater did not become lighter. The amount of body mass did not change, but the distribution of that mass changed. When the arms are extended, more mass is farther from the axis of rotation, so the body has a higher moment of inertia. It resists changes in rotation more strongly. When the arms are pulled inward, the mass moves closer to the axis, the moment of inertia drops, and the spin speeds up. This is conservation of angular momentum, and it is beautiful because you can see it with your own eyes. A slow, graceful spin becomes a blur, simply because the mass moved inward. Torque is what creates or changes rotational motion. Moment of inertia is what resists that change. And once you understand those two ideas, you begin to see machines differently. Think about a car engine. Inside the engine, pistons move up and down. That is straight line motion. But the wheels need to rotate. So the engine has to convert the up and down motion of the pistons into spinning motion. It does that with a crankshaft. The crankshaft is shaped so that the piston does not push exactly through the center of rotation. It pushes at an offset. And because the force is applied away from the center, it creates torque. The crankshaft spins. That spinning motion goes through the transmission and drivetrain and eventually reaches the wheels. When people say an engine produces 300 foot-pounds of torque, they are describing a specific amount of twisting force. A foot-pound is what you get when 1 pound of force acts at the end of a 1-foot lever. 300 foot-pounds means the engine is producing enough twist that, if you imagined a 1-foot lever attached to the crankshaft, you would feel 300 pounds of force at the end. That is enough to move a heavy vehicle from a standstill. But torque is not the same thing as horsepower. Torque is twisting force at a given moment. Horsepower is about how quickly work is being done. In an engine, horsepower depends on torque and how fast the engine is spinning. A big diesel truck may produce enormous torque at low speed. which is why it can pull heavy loads from a dead stop. A racing engine may produce less torque, but spin extremely fast, creating high horsepower. One is strong and slow, the other is lighter and faster. Different strategies, same physics. James Watt helped make this distinction practical in the 18th century. Watt was refining the steam engine, and he needed a way to explain to customers how useful his engines were, so he compared them to horses. He estimated how much work a strong horse could do in a minute and created the unit we still call horsepower. It was partly science, partly marketing, but it gave people a way to compare machines. What Watt was really helping people understand was this: a shaft turning slowly with huge torque and a shaft turning quickly with smaller torque can do the same amount of work per minute. The difference is how that work is delivered, and that is why gears exist. A small gear driving a large gear trades speed for torque. The output turns more slowly, but with more twisting force. A large gear driving a small gear does the opposite. It trades torque for speed. This is what your car's transmission does. In first gear, the engine's torque is multiplied so the car can move from a stop. On the highway, higher gears trade some of that torque for speed because you no longer need as much twisting force to keep moving. Gears are ancient too. One of the most astonishing examples is the Antikythera mechanism, a Greek device from around the 1st century BC, discovered in a shipwreck near a small island between Crete and the Peloponnese. It was filled with precision bronze gears. It worked as an astronomical calculator, tracking the sun, the moon, and possibly planets through interlocking gear trains. When modern researchers examined it, it was almost like finding a mechanical computer from the ancient world. The Greeks may not have described torque with modern equations, but they could build machines that managed rotational motion with astonishing precision, and that is something worth remembering. But engineering often begins as practical knowledge long before it becomes formal theory. People build first, then, slowly, they learn how to calculate what they have built. Now let us move from machines to structures. In mechanical engineering, we usually say torque. In structural engineering, a very similar idea is often called a moment. A moment is a force multiplied by a distance from a point. It describes the tendency of a force to rotate or bend something. And every beam in every building you have ever entered is dealing with moments. Think about a diving board. When a diver stands near the base, the board bends only a little. But when the diver walks to the far end, the board bends much more. The weight of the diver acts downward, and the distance from the fixed support creates a bending moment. The farther out the diver stands, the larger the moment. That is why the board is most stressed at the base, where it meets the platform. That is where the bending moment is greatest. If the board fails, it will usually fail there, and that is why diving boards are thickest near the support and thinner near the end. Engineers put more material where the moment is highest. This same logic appears in bridges, floor joists, airplane wings, crane booms, balconies, shelves, and skyscrapers. A beam bends because one part of it is trying to rotate relative to another part. The moment causes that tendency. The shape and strength of the beam resist it. The history of structural engineering is, in many ways, the history of learning to calculate these moments accurately enough that buildings and bridges do not fall down. One of the first people to study this seriously was Leonardo da Vinci. We know Leonardo for painting the Mona Lisa and the Last Supper. But his notebooks show a mind obsessed with mechanics. He sketched gears, pulleys, levers, flying machines, water flows, and machines of war. He also studied beams. He wanted to know how much load a wooden beam could carry before it broke. How did the answer change if the beam was longer, or deeper, or wider? Leonardo did not have calculus. He did not have the mathematics that would arrive later. But he experimented, observed, and noticed something important. A deeper beam is much stronger in bending than a wider beam. That is still one of the great practical lessons of structural engineering. If you take a flat board and lay it flat, it bends easily. Turn the same board on its edge, and it becomes far stiffer. You did not add material. You simply moved the material farther from the neutral middle of the beam, where it can resist bending more effectively. Later, engineers would discover that bending resistance depends strongly on depth. Double the depth of a rectangular beam, and its resistance to bending increases dramatically. That is why floor joists are tall and narrow. That is why steel beams are shaped the way they are. Geometry matters as much as material. Then came Galileo. Most people remember Galileo for the telescope, the moons of Jupiter, and the conflict over the motion of the Earth. But his final major work, Two New Sciences, published in 1638 while he was under house arrest, is one of the foundations of engineering. Galileo asked a deceptively simple question: why can you not just scale things up? Why can a small animal have thin legs while an elephant needs massive ones? Why can a small beam work perfectly, but a much larger version of the same shape collapse under its own weight? His answer was brilliant. When you scale an object up, its weight increases faster than its strength. Weight depends on volume, and volume grows with the cube of size. Strength depends more on cross-sectional area, which grows with the square. So if you double every dimension, the object becomes 8 times heavier, but only about 4 times stronger. Keep scaling up, and eventually, the structure cannot support itself. This is why giant ants cannot exist in the simple way we imagine them. Their legs would fail under their own weight. It is why large animals have proportionally thicker bones than small animals. And it is why engineers cannot simply enlarge a design and expect it to behave the same way. Galileo also studied cantilever beams, beams fixed at one end and free at the other, like a balcony or a flagpole. He understood that the greatest bending moment occurs at the fixed end. He understood that the beam would tend to fail there. He did not get everything right. He misunderstood some details of how tension and compression distribute across a bending beam. But he framed the problem correctly. He showed that structures could be analyzed mathematically. After Galileo, the theory became sharper. Robert Hooke discovered that materials deform in proportion to the force applied to them, as long as they are not pushed beyond their elastic limit. Pull a spring twice as hard and it stretches twice as far. Bend a beam with twice the load and it deflects more predictably. This became Hooke's law, and it gave engineers something priceless: predictability. Then Leonhard Euler studied buckling. Imagine a thin column standing upright, pressed down on the top. At first it seems fine. Then suddenly it bows sideways and collapses. The material may not be crushed. Instead, the column fails because a small sideways deflection then creates a bending moment, which creates more deflection, which creates a larger moment, until the process runs away. Euler worked out the critical load at which this happens. His formula showed that buckling depends on the column's length, stiffness, and cross-sectional shape. Long, slender columns are vulnerable. Short, thick columns are not. And this brings us to a beautiful connection. The resistance of a beam or column to bending depends on something called the moment of inertia of its cross-section. That is related to how far the material is distributed from the central axis. A hollow tube is much better at resisting bending and buckling than a solid rod of the same weight because the material is pushed outward, away from the center. That is why bicycle frames are tubes. That is why bamboo is hollow. That is why many bones in your body are not solid rods. Nature and engineering found the same efficient solution. Then Claude-Louis Navier helped pull these ideas into a coherent theory of structural analysis. He formalized how stresses distribute through beams, columns, and frames. He showed that when a beam bends, one side is in tension, the other is in compression, and between them is a neutral axis where the stress is nearly zero. The farther from that neutral axis you go, the greater the stress. That is why I-beams exist. An I-beam puts most of its material in the top and bottom flanges, far from the neutral axis, where the bending stresses are highest. The thin web in the middle connects them and handles shear, but most of the bending resistance comes from the material placed far away from the center. Every steel-framed building, every bridge, every industrial structure filled with I-beams is a physical expression of this mathematics. By the middle of the 19th century, engineers had a powerful theoretical toolkit. They could calculate bending moments, stresses, deflections, and buckling loads. But theory is only useful if it is applied correctly. And the 19th century was about to test engineering on a terrifying scale. The age of iron, steel, railways, and long-span bridges had arrived. One of the most important engineering failures in history happened on the evening of December 28, 1879, in eastern Scotland. A violent storm swept across the Firth of Tay near Dundee. In the darkness, a passenger train was crossing the Tay Bridge, then one of the longest bridges in the world. The bridge had opened less than 2 years earlier. Its designer, Thomas Bauchinch, had been knighted for it. It was considered a triumph of Victorian engineering. Then the central spans collapsed into the river. The train went down with them. All 75 people on board died. The investigation revealed a chain of failures. Bauch had badly underestimated wind loading. The bridge's tall, slender, cast iron columns were not strong enough to resist the enormous lateral forces created by the storm pushing against the bridge and the train. The wind was not just pushing sideways. Because it acted high above the base of the columns, it created a huge overturning moment. A force times a height. A moment trying to rotate the structure over. The connections were also weak. The cast iron was flawed. Bracing lugs were poorly made. Bolts loosened. Defects had been patched instead of properly recast. The Tay Bridge disaster forced engineers to take wind seriously, not as a minor afterthought, but as a major design load. It also taught a lesson that engineering keeps relearning. A structure is only as strong as its weakest connection. You can have beautiful calculations. You can have elegant theory. But if the bolts are bad, if the iron is flawed, if inspection is careless, the bridge does not care about your intentions. The bridge falls. And just a few miles away, Another bridge would soon rise in response to that disaster. The fourth bridge. If you have ever seen a photograph of it, you probably remember it. It is enormous, red, angular, and strange. Three massive cantilever towers stretch across the Firth of Forth like giant steel creatures crouching over the water. It does not look delicate. It looks almost aggressively strong. That was not an accident. After the Tay disaster, Thomas Boucher's proposed design for a fourth crossing was abandoned. The project went to John Fowler and Benjamin Baker. Baker understood the lesson of Tay deeply. He was not going to design a bridge that was merely strong enough on paper. He wanted a bridge that made its strength visible. The fourth bridge is a cantilever bridge. A cantilever is a structure fixed at one end and projecting outward like a diving board. When loaded, it creates a large moment at the support. But the fourth bridge uses balanced cantilevers. Each tower has arms extending in opposite directions. The forces on one side help balance the forces on the other. Baker famously demonstrated the principle with people sitting in chairs, holding sticks outward with their arms, while another person sat suspended between them. The seated people represented the towers. Their arms represented the cantilevers. The person in the middle represented the suspended span. It was a simple human demonstration of a vast structural idea. The bridge used more than 50,000 tons of steel and around 6.5 million rivets. Every rivet was a connection. Every connection was a possible failure point. After Tay, Baker knew that connections mattered as much as main members. Teams of workers heated rivets until they glowed, placed them into holes, held them from one side, and hammered them from the other. This happened millions of times over years of construction, in wind, cold, height, and danger. The human cost was real. Around 98 workers died during construction. That is part of the story, too. Engineering triumphs often have shadows, but the bridge stood. It stood because wind loading was placed at the center of the design. It stood because the forces were understood, because the moments were balanced, because the steel was arranged to carry tension and compression where they belonged. The fourth bridge was not just a bridge. It was a new way of thinking. Structures were no longer treated as static objects carrying simple vertical loads. They were dynamic systems interacting with wind, temperature, vibration, trains, fatigue, and time. And time is the key word. Because a structure can fail not only from one huge overload, but from millions of smaller loads repeated again and again. This is fatigue. A German engineer named August Wöhler studied this problem in the 19th century, especially in railway axles. A railway axle rotates under load. As it turns, each point on the metal surface cycles between tension and compression. One rotation is one stress cycle. Over years of service, an axle may experience millions of cycles. Wöhler discovered that metals can crack and fail under repeated loading, even when each individual load is far below the load that would break the metal in a single test. This was a profound discovery. A part can seem safe today. It can seem safe tomorrow. It can survive thousands of uses. And still, a microscopic crack can be growing quietly, one cycle at a time. Wöhler's work led to SN curves, stress versus number of cycles to failure. These curves became central to engineering. They taught designers to think not only about how strong something is, but how long it must survive under repeated stress. Fatigue matters in bridges. It matters in train axles. It matters in engines, cranes, ships, turbines, and aircraft. And in the early jet age, fatigue produced one of the most famous engineering lessons of the 20th century. The de Havilland Comet was the world's first commercial jet airliner. When it entered service in 1952, it felt like the future had arrived early. It flew faster than propeller aircraft. It flew higher, above much of the weather. Passengers described it as smooth, quiet, almost unreal. Britain was proud of it. After the devastation of the Second World War, the comet was a symbol of national technological confidence. Then it began falling out of the sky. In May 1953, BOAC Flight 783 broke apart after taking off from Kolkata. 43 people died. Investigators suspected severe weather and structural failure. Then, in January 1954, BOAC Flight 781 disintegrated over the Mediterranean near the island of Elba. 35 people died. The fleet was grounded, modified, and returned to service. Then, in April 1954, another comet, South African Airways Flight 201, broke apart over the Mediterranean near Naples. 21 more people died. This time, the aircraft was grounded permanently. The investigation that followed was extraordinary. Engineers at the Royal Aircraft Establishment at Farnborough recovered wreckage from the sea and reconstructed the aircraft piece by piece. They also placed an entire comet fuselage inside a giant water tank and repeatedly pressurized and depressurized it, simulating flight after flight. They used water because water is nearly incompressible. If the fuselage failed, it would not explode violently the way it would if filled with pressurized air. After thousands of simulated flight cycles, the fuselage failed. A crack formed near the corner of a window opening and spread rapidly through the skin. The same pattern was found in the wreckage. The comet had large, almost square windows. At the corners of those windows, stress concentrated. The pressurized fuselage was being stretched every time the aircraft climbed to altitude, then relaxed every time it landed. This repeated cycle created fatigue. The corners of the window openings, along with rivet holes and manufacturing damage, became places where cracks could begin. Each flight grew the cracks a little more. Eventually, a crack reached a critical size. The fuselage could no longer contain the pressure. The crack tore through the structure in a fraction of a second. Explosive decompression. Structural breakup. Catastrophe. The lesson reshaped aircraft design forever. Future airliners used rounded windows with generous radii because rounded shapes such as reduce stress concentrations. Aircraft structures adopted fail-safe principles, redundant load paths, tear straps, and inspection methods designed to catch cracks before they became fatal. The comet was not designed by fools. It was designed by talented engineers, working at the edge of what was known. But they had entered a new world. Pressurized jet transport, high altitude, repeated cycles, new speeds, new expectations. They discovered a gap in knowledge only after that gap became deadly. This is one of the hard truths of engineering. At the frontier, you do not always know what you do not know. From Archimedes to Galileo, from Euler to Navier, from Tay to Forth, from Voller to the comet, the same question keeps returning. How do forces move through structures? Where do they concentrate? Where does failure begin? And what must we change so that it does not happen again? In the 20th century, this question changed again because materials changed. For most of this story, We have been talking about iron, steel, and aluminum. Metals are relatively predictable once you know their properties. In many cases, they behave similarly in all directions. Engineers call this isotropic, but composites are different. Carbon fiber reinforced polymer, for example, is incredibly strong and stiff along the direction of the fibers. But across the fibers, it is much weaker. Its strength depends on direction. Engineers call this anisotropy. That means when you design with carbon fiber, you are not just choosing a material, you are designing the material itself. You decide where the fibers go. You decide what angle they follow. You decide which layers resist bending, which resist twisting, which resist tension, which resist compression. This is especially important for torsion. If you build a composite tube and lay fibers straight along its length, it may be excellent in bending, but not ideal in twisting. If you wind fibers at plus and minus 45 degrees, they become much better at resisting torsional shear. So a composite drive shaft, helicopter blade, wing skin, or Formula One monocoque can be tuned for the exact forces it will experience. This is powerful, but it is also complicated. Metals often show damage visibly. A crack forms, grows, and can be inspected. Composites can hide damage inside. A dropped tool may leave almost no surface mark, while internal layers delaminate beneath the surface. That hidden damage can reduce strength significantly. So engineers had to learn new inspection methods: ultrasound, thermography, careful damage tolerance testing. They had to prove that composites could survive decades of real service. NASA, Boeing, Lockheed, Douglas, and others spent years testing composite aircraft components. First came secondary structures like spoilers and control surfaces. They flew in real conditions, accumulated real service time, and were examined over years. The results built confidence. Eventually, composites moved into primary aircraft structure. The Boeing 787 Dreamliner became one of the clearest symbols of that transition. Its fuselage and wings are about half composite by weight. Large fuselage barrel sections are made using automated fiber placement, where robotic systems lay carbon fiber strips at precise angles, layer by layer, before curing the structure. Compared with an aluminum fuselage assembled from many panels and fasteners, a composite barrel can reduce joints and improve fatigue behavior. And because composites do not fatigue under pressurization in the same way aluminum does, the 787 could offer a lower cabin altitude than many older aircraft. That means passengers can feel slightly less tired and dehydrated on long flights. Material science changes the structure. The structure changes the cabin. The cabin changes the human experience. That is engineering at its best: invisible, quiet, and deeply practical. Composites also make possible something called aeroelastic tailoring. An aircraft wing bends under lift. It also twists. In a metal wing, that bending twisting behavior is largely determined by geometry. But in a composite wing, engineers can choose fiber orientations so that when the wing bends upward in a gust, it twists in a helpful way, reducing angle of attack, lowering the load, and protecting itself. The structure becomes self-adjusting, not intelligent in the electronic sense, but intelligent in the physical sense. Its material behavior is designed to respond to force. That would have seemed almost impossible to earlier engineers. Navier could calculate stresses in a beam. Baker could balance a cantilever. Uh, but composite aircraft allow structure and aerodynamics to become part of the same conversation. Still, even with advanced materials, the old lessons remain. Forces must go somewhere. Stress still concentrates around holes and corners. Fatigue still matters. Connections still matter. And oversight still matters. One of the strangest and most devastating examples of that happened not in an aircraft or a bridge, but in Boston on January 15, 1919. The Boston Molasses Flood sounds almost fictional. A massive steel tank, about 50 feet tall and 90 feet in diameter, holding more than 2 million gallons of crude molasses, suddenly ruptured in the north end of Boston. A wave of molasses surged through the streets. At an estimated 35 miles per hour, 21 people died. Around 150 were injured. Buildings were knocked from their foundations. The elevated railway was damaged. Horses, people, and debris were trapped in a thick, dark, moving mass that first behaved almost like a flood of water, then slowed and thickened into something almost impossible to escape. The tank belonged to the Purity Distilling Company. It had been built in 1915 to store molasses used in industrial alcohol production. From an engineering point of view, the tank was a cylindrical pressure vessel filled with a dense liquid. Molasses is heavier than water. The pressure at the bottom of the tank was much higher than near the top. That pressure created hoop stress in the steel shell, tension trying to split the cylinder around its circumference. The lower plates should have been thick enough to handle the load. The riveted seams should have been properly designed. The foundation should have been adequate. The steel should have been suitable. But the tank was poorly designed and poorly supervised. The construction had been overseen by Arthur Gell, a company treasurer with no engineering background. The tank leaked for years. Residents saw molasses seeping from the seams. Children reportedly collected it in cups. The company's response was not to properly investigate the leaks. They painted the tank brown so the leaking molasses would be less visible. That detail is almost unbearable. A huge tank full of dense liquid, in a crowded neighborhood, visibly leaking from its seams, and the solution was cosmetic. On the day of the disaster, the tank had recently been filled with warm molasses. The weather had shifted from very cold to much warmer. Fermentation gases may have added internal pressure. The steel may have been brittle in the cold. Cracks had likely been growing near riveted seams. Then the structure failed. The tank tore open near the base, where stresses were highest. Once a crack reached critical size, the steel ruptured rapidly. The contents burst outward. The investigation and lawsuit lasted years. The company was ultimately found liable. The disaster helped push the movement toward professional engineering oversight and licensing. That is one of the larger lessons of the Boston Molasses Flood. The problem was not that no one in the world understood pressure, steel, or stress. The problem was that the knowledge did not reach the decision. Engineering is not only equations, it is responsibility, it is inspection, it is certification. It is the authority to say no when a structure is unsafe. The mathematics of stress and torque do not protect anyone if the person choosing the steel thickness does not understand them, or if the person who does understand them is ignored. This pattern appears again and again. The Tay Bridge did not fall because wind was impossible to understand. The comet did not fail because fatigue was completely unknown. The molasses tank did not rupture because pressure was a mystery. They failed because knowledge, practice, oversight, and responsibility did not line up in time. Now let us come closer to everyday life. There is a structure you probably interact with more often than bridges, aircraft, or industrial tanks. A car. More specifically, a car chassis. One of the most important structural properties of a vehicle is torsional rigidity. How much the frame twists when one wheel moves differently from the others. Imagine driving over a speed bump at an angle. One wheel rises first while the others remain lower. The car's structure is twisted. If the chassis is flexible, the body shudders. Door openings distort slightly. The suspension cannot do its job cleanly because the frame itself is moving too much. If the chassis is stiff, the suspension handles the motion, and the body feels solid. Early automobiles were basically horse carriages with engines. Their frames were simple ladder structures. Two long rails connected by cross members. They were decent at carrying vertical bending loads, but weak in torsion. At low speeds, this did not matter much, but as cars became faster and heavier, chassis twist became a serious problem. Engineers first tried brute force, thicker rails, deeper sections, more cross members. But more steel meant more weight, which required more power, which created new loads. The deeper solution came from understanding the difference between open and closed sections. Take a sheet of paper and fold it into a C shape. It twists easily. Now roll the same paper into a tube. Suddenly, it becomes much harder to twist. A closed section resists torsion efficiently because shear stresses can flow around the shape in a continuous loop. An open channel cannot do that. It warps and twists more easily. Early ladder frames were mostly open channels. Aircraft designers understood this earlier because wings must resist torsion to fly safely. As airplanes moved toward stressed skin construction, the skin itself became part of the structure, forming closed torsion boxes. Automotive engineers borrowed this thinking. Vincenzo Lancia's Lambda, introduced in 1922, was one of the first production cars, with a load-bearing unitary body. Instead of a separate frame with a body placed on top, the body itself became structural. It created a stiffer, more integrated shell. After the Second World War, many engineers trained in aircraft structures brought those ideas into the auto industry. Unibody construction became common in passenger cars. Torsional rigidity became an explicit design target. Today, a modern sedan may have tens of thousands of Newton meters per degree of torsional stiffness. A sports car may have much more. A Formula One carbon fiber monocoque can be extraordinarily stiff while weighing very little, because the fibers are oriented to resist torsion precisely. You feel this engineering without thinking about it. When a car feels solid over a rough road, that is torsional rigidity. When the steering feels precise, the suspension predictable, the cabin quiet, the doors aligned, torsion has been managed. And it matters in crashes too. Modern crash structures are designed to deform in controlled ways. Crumple zones absorb energy. The passenger cell remains intact. But predictable crash behavior depends on a structure whose stiffness and load paths are understood. If the chassis twists unpredictably, crash forces may travel where they should not. So even in the ordinary act of driving to a store, you are trusting centuries of structural thinking. From Archimedes to Euler, from the fourth bridge to carbon fiber monocoques, from railway axles to suspension mounts, and now, finally, we arrive at something even smaller. something so common that it almost disappears from thought. The bolt. A bolt and nut may seem simple, but it is one of the most important engineered objects in the world. Bridges depend on bolts. Aircraft depend on bolts. Engines, towers, cranes, cars, railways, wind turbines, and machines of every kind depend on bolts. And a bolt works through controlled torsion. When you tighten a bolt with a wrench, you apply torque. The threads act like an inclined plane wrapped around a cylinder. As the bolt turns, the thread geometry converts rotation into linear motion. The bolt stretches slightly. That stretch is the secret. The bolt behaves like a spring. It wants to return to its original length. That elastic tension creates clamping force, pulling the connected parts together. A good bolted joint is not held together because the bolt simply sits there. It is held together because the bolt is stretched carefully within its elastic range. Too little torque, and the joint can loosen. Too much torque, and the bolt may stretch beyond its yield point, permanently weakening it. Or it may create uneven clamping force and damage the parts it holds. Think about lug nuts on a car wheel. They have a specified torque for a reason. If they are too loose, the wheel can work itself free. If they are too tight, studs can be damaged or brake rotors can warp. The difference between safe and unsafe may be a controlled amount of twist. But here is the fascinating part. When you torque a bolt, most of your effort does not become clamping force. Much of it is lost to friction in the threads and under the bolt head or nut. A small change in lubrication, surface finish, washer type, or thread condition can change the actual bolt tension significantly for the same applied torque. That is why torque specifications often depend on whether threads are dry or lubricated. In critical structures, engineers sometimes do not trust torque alone. They may measure bolt stretch directly. They may use ultrasonic methods. They may use turn-of-nut procedures where the bolt is tightened snug and then rotated a precise additional amount. Some fasteners are designed so part of the head shears off at a target installation torque. All of this exists because torque is only an indirect way of creating what really matters: tension in the bolt. And bolts, like axles and aircraft skins, can suffer fatigue. A bolted joint experiences vibration, temperature changes, bending, and repeated loads. The first engaged thread often becomes a stress concentration. Tiny cracks can form at thread roots. Over enough cycles, they can grow. Wohler's railway axle problem lives inside the bolts that hold modern machines together. That is one of the most beautiful things about this entire story. The same principles keep returning at different scales. A lever in ancient Syracuse, a wooden beam in Galileo's imagination, a steel column in a Scottish storm, a riveted cantilever bridge over the Firth of Forth, a pressurized jet airliner over the Mediterranean, a molasses tank in Boston, a carbon fiber wing, a car chassis twisting over a pothole, a bolt being tightened by a mechanic. Different objects, different centuries, same invisible language of force, distance, material, geometry, and time. Engineering knowledge accumulates slowly. Archimedes understood the lever. Leonardo studied beams and mechanisms. Galileo saw why scale changes everything. Hooke gave engineers elastic predictability. Euler explained buckling. Navier formalized bending stress. Wohler revealed fatigue. The Tay Bridge taught the importance of wind and connections. The fourth bridge showed what conservative, visible strength could look like. The comet taught the danger of stress concentrations and repeated pressurization. Composites taught engineers to design the material itself. The Boston Molasses Flood reminded the world that knowledge is useless without responsibility, and every generation added something. Not all at once, not perfectly, often through failure, often at great cost, but the knowledge remained. It moved into textbooks, standards, inspection rules, design codes, certification tests, manufacturing processes, torque charts, finite element models, and the quiet habits of engineers who check details most people will never notice. Somewhere tonight, an engineer is running a simulation of torsional stress in a new structure. Somewhere else, a technician is calibrating a torque wrench. A mechanic is tightening wheel bolts to specification. A bridge is flexing under traffic. An airplane wing is bending gently in smooth air. A skyscraper is swaying slightly in the wind. A car frame is absorbing a bump in the road. A door hinge is carrying the small moment created every time someone walks into a room. The world is full of torsion, quietly doing its work. And perhaps that is a comforting thought, because every object around you that holds weight, resists motion, carries load, or keeps parts together represents a long chain of human understanding. Not perfect understanding, not effortless understanding, but earned understanding. People observed, they tested, they calculated, they failed, they rebuilt. They wrote standards, they improved materials, they learned where cracks begin, where beams bend, where columns buckle, where tanks rupture, where windows concentrate stress, where bolts stretch, and where bridges must be stronger than anyone first imagined. Torsion is only one thread in that enormous tapestry, but it runs through almost everything. From the simplest hand tool to the most advanced aircraft, from the crankshaft of an engine to the double helix of a drill bit biting into steel, from a child's spinning top to a satellite's reaction wheel, from a car chassis to a bridge connection, from the wrench in your hand to the wing above the clouds. The forces are always there, twisting, turning, pulling, bending, cycling, waiting, and the engineers are there too, mostly invisible, making sure the frame holds, making sure the joint stays tight, making sure the bridge can meet the wind, making sure the window corner is rounded, making sure the fibers lie in the right direction, making sure the bolt is tightened just enough. That is why this story is not only about one force. It is about the hidden language structural engineers use when they look at the built world. A bridge is not just a bridge. It is tension, compression, shear, bending, torsion, fatigue, vibration, material choice, connection design, safety factors, and human judgment working together. A building is not just walls and floors. It is a negotiated peace between weight, wind, ground, temperature, water, people, and time. So tonight, wherever you are, whatever you are resting on, torsion is at work somewhere near you. In the hinges of your doors, in the fasteners inside the walls, in the frame beneath the floor, in the vehicle outside, in the machines that built the room around you. It has been understood, accounted for, managed. You can let your thoughts unwind. Let the tension in your own body release and rest. The engineers have done their work. The math checks out. The bolts are tight.